Have you ever imagined an engine without a chain, without a camshaft? Yet, it can still open and close its valves on its own, and even the engine itself rotates along with the propeller. Pretty amazing, right? Today, we're going to talk about one of the most unique engines in aviation history, the Gnome Rotary engine. This engine has an unusual design and operates in a way that's completely different from the conventional engines we're more familiar with. Not only does the propeller spin, but the entire engine rotates along with it. What's incredible is that this unique feature offers several advantages, including a lighter weight, better stability, and higher efficiency. Made in France, this engine was a key player during World War I and brought groundbreaking innovations to the world of aviation. Now, the question is, why was this engine designed to rotate? And what are its pros and cons compared to conventional engines? Before diving into the mechanism and advantages of the Gnome Rotary engine, we need to understand its development. Every innovation has an interesting backstory, and this engine is no exception. Who was its creator? What inspired its design? And how did it evolve in the world of aviation? Let's rewind a bit, all the way back to the 19th century, the Gnome Rotary engine. Behind its name, there's the story of three brothers, Louis, Laurent, and Augustin Séguin. They were the grandsons of the famous engineer Marc Séguin. In 1906, Louis founded Société des Moteurs Gnome. Initially, the company produced stationary engines for industry, licensed from the German company Motorenfabrik Oberursel. But they didn't stop there. Louis, along with Laurent, began designing an engine specifically for aircraft. Their first experimental engine was a 5-cylinder model with 34 horsepower. This engine was still a radial type and lacked the distinctive features we know today. It wasn't until later that they discovered the advantages of rotary engines when it came to cooling. From this, the Gnome Omega was born, a 7-cylinder engine with 50 horsepower. This engine was introduced at the Paris Motor Show in 1908, and it's still on display at the Smithsonian National Air and Space Museum today. The Gnome Omega was the world's first production rotary engine, and it immediately captured attention. This design became the most widely used during World War I. In fact, the German version of this engine was used in the Red Baron's fighter planes. So, what makes this engine so special? This engine has valves that are directly mounted in the pistons and operates entirely automatically, without any external commands. What's unique is that this engine doesn't require a chain or camshaft. Instead, it uses 2 mesh counterweights equipped with springs. The valves open and close on their own, thanks to a clever internal mechanism. It's also quite large, almost the same size as the piston diameter itself, allowing for extremely fast gas exchange. Additionally, there's an L-shaped ring, and the entire engine rotates, while the crankshaft remains stationary. The advantages are quite clear. Back then, engines could only generate small amounts of power and required a very heavy flywheel to operate optimally. Weight was the biggest enemy for aircraft. Gnome tackled this issue by eliminating the flywheel and replacing it with the rotating weight of the crankcase and cylinders. The vibrations produced are also smaller compared to conventional radial engines because the pistons rotate along with the engine. With an 8-liter capacity, 7 cylinders, and large intake and exhaust valves, this engine was designed for optimal power output. Combined with a long piston stroke and a compression ratio of 5:1, it generates 50 horsepower at 1,500 RPM. Now, this raises a question. Are there any other engines with a concept similar to the Gnome Rotary engine? For comparison, there's the Ford T engine, which has a 2.9-liter capacity and only generates 20 horsepower. If the Ford T engine were scaled up to 7 liters, its power output could come close to that of the Gnome Rotary. However, the Ford T still requires a radiator-based cooling system with coolant to maintain the engine's operating temperature. This is in contrast to the Gnome Rotary's design, which relies on air cooling, making it lighter and simpler without the added weight of a radiator and coolant. The Gnome Rotary engine had a unique design where the entire engine rotated along with the propeller shaft. This motion created a high-speed airflow that was extremely effective at cooling the cylinders, eliminating the need for a radiator or any other liquid cooling system. As a result, the overall weight was significantly reduced, making it ideal for early 20th century aircraft. Another distinctive feature was that the propeller was mounted directly onto the engine and rotated along with it. At the time, the understanding of propeller aerodynamics was still limited, but it was already known that the tips of the propeller should not exceed the speed of sound. If they did, shock waves would form at the tips, causing a loss of efficiency and potentially damaging the structure of the propeller itself. Additionally, the size of the propeller was restricted by the distance between the aircraft and the ground. Taking these factors into account, a rotational speed of 1,500 RPM was considered ideal to balance power output, cooling, and propeller efficiency. The rotary engine's design proved to be a brilliant solution to the challenges faced by conventional engines at the time, thanks to its radically different approach. Instead of moving pistons up and down inside a stationary block, this engine spun the entire block, creating a natural cooling effect. Now that we've explored its history and unique design, it's time to dive into how this engine actually works. What exactly makes it so different from conventional engines? And why did the entire engine need to rotate? First, there's a hollow crankshaft that connects directly to the aircraft's body. At the front of the engine sits a carburetor, which mixes air, fuel, and oil before feeding the mixture through the crankshaft into the crankcase. Inside the crankcase, passages distribute the oil, spraying it into various parts of the engine. The crankcase itself not only houses the internal components, but also acts as the main channel for delivering the air-fuel-oil mixture. The crankcase is connected to the crankshaft via a bearing, allowing it to spin freely. Next, there's a master connecting rod, along with several slave connecting rods. Each connecting rod operates a piston, and each piston is equipped with an automatic intake valve. These automatic valves work using a counterweight and spring system. As the piston rises and rotates downward, the vacuum created opens the valve. Then, as the piston begins moving upward again, inertia and compression pressure automatically close the valve. Cooling fins are mounted on each cylinder to help dissipate heat. At the top of each cylinder is a large valve secured with a threaded fitting, making it easy to remove for maintenance. The valve is operated by a rocker arm and pushrod system to ensure optimal opening and closing. The camshaft is hollow and spins over the crankshaft at half the engine speed, controlled by a gear system. If you look closely, the cam follower completely encircles the cam in a D-shaped profile. This setup works similarly to the desmodromic system used in Ducati motorcycles, mechanically opening and closing the valves in one continuous motion. Such a system is necessary because of the large size and heavy weight of the valve assemblies. Since the entire engine is spinning and subjected to centrifugal force, any imbalance could cause the valves to open unintentionally at high RPM. However, thanks to this design, that risk is prevented. Additionally, to accommodate expansion and other tolerances, the valves are equipped with springs to ensure they stay tightly sealed. Each cylinder is also equipped with its own spark plug, which is connected to the ignition system through a series of wires. The carburetor on this engine always operates at full capacity. Although there is a mechanism to adjust the amount of incoming air to achieve a better air-fuel mixture, in practice, the throttle, butterfly valve, does not directly control the engine speed. This is mainly due to the limitations of the simple fuel nozzle design, which couldn't atomize the mixture effectively. Moreover, the carburetor lacks both a float chamber and a venturi, so it must operate at full flow to function properly. While the mixture can be adjusted slightly to slow the engine down, the most effective way to control power was to cut off the ignition. The pilot could press a blip switch to interrupt the ignition across all cylinders at once. However, even with the ignition cut, the engine would still receive a full supply of unburned fuel, which would simply be expelled through the exhaust, leading to significant fuel wastage. While not ideal, this method of power control was primarily used during landing. It's also important to note that at the time, engines weren't producing very much power, and aircraft speeds were relatively low, so there was little need to reduce engine output during flight. As a result, the throttle was almost always kept wide open. Now, the question is, does this engine operate on a 2-stroke or 4-stroke cycle? Now, let's imagine that the crankcase remains stationary and only the crankshaft rotates. To make it easier to explain, we'll focus on just one cylinder. First, the mixture of air, fuel, and oil flows through the hollow crankshaft. As the piston moves downward, it creates a low-pressure area, vacuum. This vacuum opens the intake valve, allowing the mixture to enter the cylinder. Once the piston passes bottom dead center, inertia and compression pressure cause the intake valve to close again. At this point, the compression ratio reaches 5:1. Next, the spark plug ignites the air-fuel mixture. The high pressure from combustion ensures that the intake valve stays closed. Afterward, the exhaust valve opens, allowing the burnt gases to exit the cylinder. This cycle continuously repeats through 4 main stages: intake, compression, combustion, and exhaust. Therefore, it's clear that this engine operates on a 4-stroke cycle. When we observe the engine from the outside, it's clear that ignition only occurs when a piston reaches top dead center. This follows the principle of a 4-stroke engine, where one cylinder fires while others are either compressing, exhausting, or intaking. This is because a 4-stroke cycle requires 2 full revolutions to complete 1 power stroke. On the left side of the engine, we can see the combustion and intake strokes, while on the right side, we see the compression and exhaust strokes. The firing order starts with the odd-numbered cylinders, 1, 3, 5, and 7, then continues with the even-numbered cylinders, 2, 4, and 6, with about a 2-second interval between each ignition. From this perspective, we can clearly observe the pistons moving from top dead center to bottom dead center and back again. It gives us a much better view of the working mechanism without any parts blocking our sight. Considering that lubrication systems at the time were still very basic, the engine is equipped with bearings on almost all moving parts. This helps reduce friction and improves the durability of its components. Now, let's move on and talk about the piston rings. Why are the piston rings on this engine shaped like an L? Each cylinder is equipped with cooling fins made from nickel-plated steel. Even so, they remain lightweight, less than 5 pounds, or about 2 kilograms per cylinder. The cylinder walls are also very thin, measuring only about 0.1 inches, or roughly 2.5 millimeters thick. However, due to heat and wear over time, these cylinders can deform. After around 20 hours of operation, the entire set of cylinders originally needed to be replaced. To address this issue, the engine uses L-shaped piston rings. This design remains flexible, allowing the ring to adapt to changes in the cylinder shape caused by wear and thermal expansion, while maintaining a tight seal for combustion pressure. Thanks to this innovation, the pressure inside the cylinder stays stable, ensuring efficient combustion. As a result, the engine's service life significantly increased, from just 20 hours to around 80 hours of operation before requiring cylinder replacement. Although the Gnome rotary engine had many advantages, such as its lightweight and efficient design, it was not without flaws. One major issue with engines that used valves located in the pistons was that the counterweights could seize up. If this happened, the engine had to be completely disassembled for repairs. To solve this problem, the piston valve design was eventually replaced by a more conventional setup, a standard piston combined with ports in the cylinder wall. This updated engine became known as the single valve type, or Monosoupape in French. In the Monosoupape engine, ports were positioned near the bottom of the cylinder. As the piston moved downward, a vacuum was created, and fresh gas was quickly drawn in as the piston uncovered the ports. However, this design introduced a major risk. During the combustion stroke, when the piston reached bottom dead center, flames from the combustion chamber could potentially escape through the open ports and ignite the fuel-air mixture inside the crankcase. If that happened, the entire engine could explode violently. It's important to note that the cylinders were made from very thin, lightweight steel. To prevent pressure buildup or flame leakage, the exhaust valve was designed to open earlier. With a large exhaust valve, combustion gases could escape freely, reducing the internal pressure by the time the piston reached bottom dead center, thus minimizing the risk of explosion. After that, the piston began moving upward again, pushing any remaining exhaust gases out of the cylinder. At night, since the engine wasn't equipped with an exhaust manifold, flames shooting from the cylinders were clearly visible. It looked impressive, but also a little terrifying. However, there was another consequence to this design. The engine's power output was slightly reduced because the combustion stroke wasn't fully utilized. Even so, this design proved to be far more reliable than the earlier piston valve engines, resulting in longer intervals between overhauls. It's also worth noting that the engine featured 36 narrow ports around each cylinder. Given that the cylinder walls were only about 2.5 millimeters thick, it was clear that these ports couldn't deliver an efficient supply of fresh fuel-air mixture on their own. To solve this, the intake valve was intentionally left open for a short moment after the exhaust stroke was complete. This allowed fresh air to enter the cylinder. As the piston traveled up to about 2/3 of its stroke, the valve would close, creating a vacuum inside the cylinder. Then, as the piston moved past the ports, this vacuum would help draw in as much fuel-air mixture as possible. Jada. It's important to note that the fuel-air mixture entering the cylinder was extremely rich, with an unusually high concentration of fuel. This mixture would then blend with the fresh air already inside the cylinder, resulting in an ideal balance for combustion. As we can see, the single valve in this engine served two main functions: controlling the exhaust of combustion gases and allowing fresh air into the cylinder. This is why the engine became known as the Monosoupape, or single valve. In later versions, the problem was addressed by adding ports that connected directly to the outside of the cylinder. Further innovations included adding an extra intake valve at the top of the cylinder, equipped with its own air intake duct. This development led to the creation of the Gnome engine, which featured a unique design where a single pushrod operated two separate valves. The rocker arm system was designed to move back and forth, selectively pressing down on either valve as needed. This design was a highly efficient innovation, helping to reduce the overall weight of the engine. With 9 cylinders, the engine produced up to 90 horsepower. It was also equipped with a throttle on the carburetor, allowing for better power control and improved fuel efficiency. A German version of this engine was famously used by the legendary pilot, the Red Baron, during World War I. Due to the gyroscopic effect created by the rotating cylinders, aircraft powered by this engine could turn left very easily, but turning right was much slower and more difficult. Additionally, fuel and oil consumption was extremely high, making the aircraft more suited for short-range missions. For long-distance flights, pilots had to carry large amounts of spare fuel and oil, which ultimately negated the engine's advantage in lightweight design. If you pay attention, the rear of the aircraft appears shiny due to oil splashes coming out, along with the exhaust gases from the exhaust pipe. This happens because the Gnome engine does not use a closed oil disposal system, so most of the lubricating oil is directly expelled into the air after lubricating the engine. The oil carried by the exhaust gases then sticks to the aircraft's body, giving its surface a glossy appearance. Additionally, when the pilot activates the blip switch to momentarily cut off the ignition, the unburned fuel mixture can accumulate in the exhaust pipe. If this mixture ignites, flames can shoot out of the exhaust pipe. This situation is very dangerous, especially for wooden aircraft that are highly flammable. The Gnome engine itself consumes about 10 liters of castor oil per flight hour. Castor oil is a natural oil extracted from castor bean seeds. With its high viscosity and resistance to extreme heat, this oil was ideal for lubricating early engines. It is from the use of this oil that the lubricant brand we know today, Castrol, was born. Interestingly, the Gnome engine also shows some similarities with a two-stroke engine. The crankcase is used to hold a mixture of fuel and oil, and there are small ports to support the flow of this mixture. However, for a radial engine to truly operate on a two-stroke principle, additional pressure within the crankcase is needed. This could only be achieved with the aid of a compressor or a turbo, which were not commonly used at the time. In a four-stroke engine, The vacuum needed to suck in the air-fuel mixture is created by the downward movement of the piston. On the other hand, if a two-stroke engine does not use a turbo, each cylinder must have a separate crankcase, something that is almost impossible to implement in a radial engine. Over time, rotary engines began to be abandoned and replaced by fixed radial engines. These new engines offered more power, more efficient oil consumption, better air cooling systems, and higher durability. As a result, rotary engines were slowly forgotten. However, in their time, these engines were the best innovation. Even to this day, we are still amazed by their unique operation, fast rotations, and distinctive sound. In the past, there was even a motorcycle that used a small rotary engine mounted directly on the front wheel. Additionally, there was a variant of this engine that featured roller cam followers. Well, that's the discussion about the legendary Gnome Rotary engine. Although it's no longer in use, this engine holds an interesting story with a design that was unique yet highly innovative. It not only changed the way airplanes flew, but also gave us valuable lessons about creativity in the technological development of the early 20th century. If you enjoyed this discussion, don't forget to like and share this video with your friends. If you have any comments, suggestions, or questions, feel free to write them down in the comments section below. See you in the next video, and thanks for watching!